because today we are having 50th lecture in this distinguished lecture series. So this is a unique sort of achievement for our group here. INAE Bhubaneswar chapter, IIT Bhubaneswar, NISER Bhubaneswar, IMMT Bhubaneswar, and of course SOA University and IEEE Bhubaneswar chapter. With our joint effort, we could really achieve this milestone, and future also it will continue. There are a number of good speakers on the line, so there will not be any difficulty in continuing it. So today we have with us Professor Josna Datta Majumdar, who is serving in the Department of Metallurgical and Materials Engineering as the Institute Chair Professor. Our area of specialization are laser materials processing, surface engineering, corrosion, and wear. She has supervised 17 PhD students, publishing 250 papers in peer-reviewed journals, 8 book chapters, and edited 1 book. She conducted sponsored research projects worth over ₹10 crores, developed full-fledged laboratory for laser plasma public spray coating. She received several prestigious science and engineering research board, fellowships and awards like Power Fellowship in 2021, awarded by the Science and Engineering Research Board, Friedrich Wilhelm Best Research Award under Alexander von Humboldt Foundation 2015, MRSI Medal awarded by the Materials Research Society of India in 2013, Metallurgist of the Year award by the Ministry of Steel India 2012, Boycast Fellowship by the Department of Science and Technology 2004, Young Engineers Award by the Indian National Academy of Engineering in 2003, Young Metallurgist of the Year by the Ministry of Steel, Government of India 2000, Young Scientist Award by the Indian Science Congress Association in 2000, and elected as the Fellows of the International Advanced Association of Materials, Sweden, and Indian National Academy of Engineering 2021, Features of Engineers 2017, and West Bengal Academy of Science and Technology Award 2016. And I also understand that very recently she has been elected as a fellow of National Academy of Science. So
thank you very much, sir. It's indeed a great honor for me to
just a minute, Professor Majumdar. So far as actually the talk is concerned, its abstract is already with you, and she will definitely explain more, and I don't have to repeat those parts. But one thing that I will seek your permission, Professor Majumdar, that we are planning actually to publish all these 50 lectures in a form of a booklet where all this, where your abstract, biodata, everything will be given, including your photograph, and the lecture is being recorded. If you permit, then we'll give us a YouTube link of your entire lecture. So anybody who is interested, he can really see. Do you have your permission?
Yes, sir, why not? It would be nice. But this, if you just say about this PPT, I have collected some of the information from open sources. So in that case, I'll just edit it a little bit by just writing the these sources, and then I'll give it to you. But otherwise, recording is not at all a problem. But if you talk about PPT, I'd like to edit a little bit and then hand it over to you.
That is okay. Then recording part actually will be interested. So the other part definitely you can send, and this we can really publish in a novel way, though where we don't have to spend much time or effort, but still the material will be having wide circulation. Okay.
Yes, sir. Thank you so much.
Thank you so much.
Yeah,
So, madam, you can now make your presentation.
Okay, sir. Thank you very much for such a nice introduction. And first and foremost, I would like to apologize that on 4th you already circulated, but I thought I would be returning back on 4th, but I was held up in Bhopal. There was another meeting which I organized over there, so I came back on 5th only. So I could not deliver the talk on 4th. So thank you very much once again.
We can understand that thing. Please go ahead.
Okay, sir. Thank you very much for inviting me and giving me the opportunity to deliver our experience on increased lifetime of bioimplants, particularly stainless steel and titanium based implants by surface engineering. So recently we have also started working on magnesium based implants, and also very few important results which we have recently just had it in the laboratory. I am not going to just talk on that because of paucity of time, but I would be delivering a little bit, you can say, abstract of what kind of work we are doing over here. So bioimplant is very important materials used to replace actually damaged part of human body. Particularly, there are different types of bioimplants, and we are mainly working on the implants which are used for hard tissue replacements, particularly dental implants, hip and femoral implants, knee prostheses, and acetabular lumbar disc replacement. So pacemaker also. This whatever approach we are following may be applied for the on the final products which are used for these applications. But certainly I must say that because of shortage of laboratory facilities, or maybe we didn't find very good collaborator for doing in vivo or clinical studies, so our all results are confined to the laboratory scale only. For upscaling it, we need a little bit more work, which I am trying to write a big project now, where we would be able to do these all kind of clinical studies and subsequently marketing these all work. And these approaches which we are following, that may be applied on finished bioimplant which are already in the market to increase its lifetime. Now, if you talk about the classification of bioimplant, so bioimplant materials may be classified into 4 different categories, like biotolerant, bioinert, bioactive, biodegradable. This is for the beginners, so this is very important and very basic classifications. So biotolerant materials are those materials which are not adverse to human body, but whenever you just implant it in the human body, there is fibrous tissue growth and they just remain like that only. Bioinert materials, similarly, they don't cause any adverse or toxicity effect on the human body, and there is by growth of there is cell adherence and growth with time. And bioactive materials are the important materials which basically promotes that cell growth and subsequently tissue growth to a very large and nice extent. And biodegradable materials are those materials which degrades within human body, and then by the cell grows and also it degrades, so it remains in the body. So it doesn't cause any toxic effect or anything, but it remains in the body, gradually degrades, and tissue and cell growth is replaced by tissue and cells. So implants are basically replaced by tissues. So like magnesium is a very nice biodegradable materials for implant applications. So these are different types of, like gold is biotolerant, then porous structure of high hydroxyapatite, it's highly bioactive in nature. Similarly, plasma straight hydroxyapatite, zirconia is actually also bioinert in nature. Then different metallic implants are bioinert in nature. So we are mainly working on the metallic implant materials, particularly Ti6L4V, AISI316L stainless steel, cobalt, chromium, molybdenum alloy, and also magnesium based alloy. And these particular metallic implants are having certain advantages over the ceramic as well as polymeric counterpart, like they are having a very high strength, they are having very good toughness, they are formable. So they are also having very better superior fatigue performance than that of ceramic materials, which are highly brittle in nature and very high strength to weight ratio. That's why they are really a little bit popular these days, getting popularity. However, problem with the metallic materials are that whenever you implant metallic materials in the human body, none of the materials are highly non-reactive in nature. Though titanium is having very good corrosion resistance, but you just keep it in the human body environment for a long time, there is gradual release of the metallic ions in the human body, leading to toxicity effect and several other problems in the human body. So the requirement for why these four materials are metallic materials are used as bioimplant, because of their biocompatibility, good osseointegration property, and comparatively higher corrosion resistance than other materials, metallic materials which are available in nature, and they are having good fatigue property, adequate strength, good Young's modulus, and also high wear resistance property. So these are the advantages and disadvantages as I stated here. So but whenever you talk about that applications of this metallic implant, they are mostly applied for heart tissue replacements, like cardiovascular devices and orthopedic devices like bone fixation, artificial joints, then dentistry, then craniofacial this thing plates and screws, then orthoneurology, artificial eardrum. So these are the different places where metallic implants are applied. And if you see there, if you compare their properties, they are also having gradation in terms of the fact that you cannot use or maybe all metallic materials do not perform in a similar fashion as implant. Like if you compare 316L stainless steel to that of titanium, you'll see that titanium is more expensive than Ti6L4V, more expensive than AISI 316L stainless steel, but AISI 316L stainless steel is having higher Young's modulus, and hence there is a problem of stress shielding which is not there in titanium. Similarly, if you talk about that minimization of stress shielding, your choice should be magnesium, but magnesium is having a very poor corrosion resistance property. So whenever they are used in human body, there is a lot of hydrogen evolution. So those problems are there. So if you talk about corrosion resistance property, titanium is based, and then 316L stainless steel, then magnesium and its alloys. But on the other hand, if you talk about strength and percentage elongation, the titanium and steel, they are of the similar category. I mean, of the same they perform in the same level. However, if you just talk about density is much higher for steel over chromium molybdenum alloy as compared to that of titanium and its alloys. So these are the different applications like joint replacement parts, bone fixation materials like nails, screws, nuts, plates, housing devices for pacemakers and artificial heart valve, surgical instruments and components, dental implants, and healthcare goods like wheelchair, artificial limb, artificial legs. These are the different places. Earlier, artificial legs used to be they fabricated by ceramic materials, but now metallic materials is coming into the market. So for this particular application, now, even though it's very popular as implant materials, however, it has been observed that it often undergoes metallic implants often undergo premature failure. So you design the implant material for certain period of time, but you see that it basically fails even before its designed lifetime. So what are the reasons? Reasons are wear, corrosion and inflammations, fibrous encapsulations, low fracture toughness, low fatigue strength, mechanical failure, and mismatch in the modulus of elasticity between the bone and implant, leading to stress sealing effect, and as a result of which you will find that there is sealing of stress surrounding the that implant material, leading to just damage of the cells surrounding it, as a result of which cells cannot survive. So this is typical example of the dental screw, which is made of TI6L4B, or maybe these days people are using TI6L4B. Earlier days people also used to use AISI316L stainless steel. So if you just insert it, you will find that there are, after certain period of time, there are so many different problems which you encounter. Particularly biggest problem is the film formation, biofilm formation, or biofouling corrosion you can say. So there is a very fine, very thin film formation consisting of biological materials surrounding this particular implant materials. And also there is because of the, in addition to that, there is also typical crevice corrosion, as well as the tribocorrosion phenomena due to constant interaction of the, due to constant chewing action during the processing actually. So you cannot keep yourself rest after implantation. At least after 4 or 5 days you have to go on having your own activity. So if the chewing action is more, then you will find that there would be more problem of the tribocorrosion, and there is also ocular overload. And then there is this, subsequently what happens is that because of this tribocorrosion and corrosion phenomena, there is always very fine, gradually you'll find that fine titanium particles are coming out, and they basically go on spreading all throughout the tissues of the human body, causing inflammation action, allergic reaction. These problems are always there in the human body after implantation, for after 5 to 6 years of implant. So these are the typical examples where you have mechanochemical failure like fretting corrosion at the interface of the, this is fretting corrosion is another kind of corrosion which is persisting in dental implant. And then TMJ implants, HIP implants, again wherever there is very I mean oscillating motion between the two surfaces, and there is another surface is solid, there is fretting corrosion, fretting where these problems are there, and which causes more accelerated rate of degradation of the metallic materials. So these are different types of corrosion that usually are encountered by AI316L stainless steel, specifically because titanium is having little higher corrosion resistance. So if you talk about titanium, titanium does not undergo pitting corrosion, or maybe it doesn't undergo like intergranular corrosion to a large extent, but it undergoes typical biofouling corrosion, and also that crevice corrosion, tribocorrosion. But different forms of corrosions are there depending on the environment and the situation. The corrosion behavior, corrosion mode changes from one mode to different, and in individual mode there is individual kinetics which occur. It is very much dependent on the that pH of the environment, depends on the kind of load the this implant is experiencing, and the kind of this motion is there, movement is there. So everything play important role. It is very difficult to simulate the situation what's happening, but mostly it has been observed that fretting corrosion is the predominant mode of corrosion, in addition to tribocorrosion in fretting mode, so which cause maximum problem associated with dental implant. But if you talk about hip and femoral prostheses and knee joints, they are mostly the in addition to corrosion, fatigue problem is also there, which cause degradation or premature failure of the implants. So this is the connecting tissue near stainless steel bone implant with integration of corrosion products. If you see all the tissues, they are covered with the corrosion product. So So barely it is carrying the corrosion product. Means if you talk about 316L stainless steel, there is chromium oxide corrosion product which just film, which basically dissolves gradually. Sometimes there is dissolution of nickel as well, which is highly toxic in nature. So this causes these all that oxide product as well as ions cause typically inflammation, as well as it cause allergic reaction, which subsequently is not good for the human health too. This is fretting corrosion, that fretting wear and fretting corrosion at the contact area of stainless steel screw hole and AISH316L plate. So you see that this is the fretting wear part. So whenever there is fretting wear, you will find that there is a discontinuous removal of the material from the surface. So it's not continuous but discontinuous removal, and there are always some kind of band formation because of the loading action. And if you talk about fretting corrosion, again you will see the similar situation but dissolution of the material from the surface. And similarly, heavy fitting corrosion. So these are the typical. This is also another interesting area where a lot of works need to be conducted, because we are trying to also gather information on the mechanism of failure of the implants, so which are not available in details in the all handbook, because the problem of getting the failed implants. So whenever I talk to the hospital, they said that whenever it fails, they basically don't consider that, they throw it away. There is no scope of keeping it, because the whenever that patient they report, then there is always a kind of lot of conflict. They don't, they try to scold the patient that possibly because the patient didn't take extra care, that's why the implant failed. But on the other hand, failure might also occur because of the materials problem, but they are not so aware of the materials and other things, because those are supplied by the those are outsourced. Actually they don't develop by their own, they have no idea about hospital doctors, they have no idea about the kind of materials they are using, because they just place the order and get the implant. So they had no idea about there could be failure because of material. So now we are trying to do one small and big project in collaboration with some hospital in Bhopal, where we will try to gather the failed implants and see what are the reasons for the failure of many implants for different applications. So now if you just talk of that the failure, these all failures, if you see, you'll find that most of the failures they are because of either fatigue failure, or maybe fretting, or maybe the combinations of fretting and corrosion, or maybe corrosion and wear. So these are the few reasons for the failure of the premature failure of the implant material. So these all failures may be overcome, or it can be overcome by typical designing of the surface. Another problem associated with the implant is that there is a scar formation at the interface. So particularly when you talk about pure metal without doing any kind of bioactive coating, if you insert in a human body, you will find that typical mechanism of the cell or tissue growth is by mechanical anchoring. So if the surface is not properly prepared or sensitized, you'll see that the cells are not growing properly, and as a result of which there is fibrous tissue growth on the surface, and which is again not good for the health. So then it basically that at the interface between the implant and that of tissue, there is cancerous cell growth. So it doesn't, it's not really good for the health in long run. So you have to prepare the surface. This is surface preparation is must. And the way usually what people, what doctors do, or what that implant manufacturers they do, is that they develop the implant and then fabricate the implant, and then they go on applying very thin layer of hydroxyapatite coating or bioglass coating, which is bioactive in nature, and they use it for the implant purpose. But the bioactive materials which they apply on the surface, they are the way they prepare or they develop the coating, that's not really so much strong coating. So whenever they insert, they assume that for this within this time period there will be cell growth. So after that, if the coating fails, it doesn't matter. So, but on the other hand, they haven't applied good coating technique for development of coating which are strong and durable in nature. And also we are basically trying to focus on two important aspects. One is osseointegration part, that is promote the cell growth on the surface of implant. Second problem which we are trying to solve is the wear and corrosion problem. So we are so this is very important. These are very important problems which need to be addressed actually. So in all cases we use the typical titanium based implant. Obviously we initially we develop the coating and see the feasibility of coating development and optimization of parameters for development of coating on coupons, and then we just check the feasibility of application of that coating in the implants which are available on the market in the market. So this is typical diagram which shows that in materials processing, actually processing, characterization and properties, they are very much dependent. They very much they do dictate very much the performance, or maybe performance of any component. It's basically influenced by the processing route which is followed, and the subsequently the properties which are achieved actually. So and structure too. So structure property correlation is very important theme of the research of the group. So we try to fabricate it by different ways and then observe the structure. Structure means structure at different scale, and then we also evaluate the property. So by just correlating structure property, we optimize the process parameters, and under optimized process parameters we try to understand the performance of the coated implant or coating. So this is typical research studies where they just did that typical this percentage of like nickel sensitization in the population as a function of year for AISA 316 stainless steel implanted patients. So they saw that this nickel sensitization is really too high for in case of females, and that is a kind of statistical information on the harmful effect of nickel. So this diagram is for 316 stainless steel, L stainless steel, which gives you information about different phase, stability of different phases as a function of composition and that of chromium and nickel equivalent. So this is not really so important, but this is very much it's a established diagram, but it's this diagram says actually what AISI 316L stainless steel is very important category of stainless steel because its microstructure is austenitic in nature, but presence of nickel causes problem because of its leaching, and people are trying to develop nickel free stainless steel by addition of nitrogen, because nitrogen is another alloying element which also stabilizes the austenite, but this is also hence it can be used for replacement of nickel for getting the similar structure. So this nickel equivalent is shown as a function of nitrogen, that carbon, nickel, chromium, nickel, cobalt, manganese, nitrogen, carbon. So as you go on increasing nitrogen content, you get similar effect as that of nickel, but without nickel. So you can cut the nickel content in steel, add more nitrogen, and have nitrogen bearing steel having the similar structure, similar properties, but it is free from nickel. So this is very important. So there are large number of nickel free stainless steels are coming into the market where the properties are similar, but they are containing nitrogen. So nitrogen is usually purged while process preparation of the steel, and during that process you can reduce the nickel content a little bit. So that chemical is some of the stainless steel implants for surgical applications, where we have where it is seen that there is a lot of nitrogen content, particularly 0.25 to 0.5, 0.85 to 1.1%. Like these are different grades actually. So here if you just check carefully, here normally in the stainless steel AS16L stainless steel, there is 18 chromium, 8 nickel. Nickel content goes as high as 11 to 13%. But in nitrogen containing steel, where nitrogen level, if it reaches, it goes up to 1.1 or 1%, you can reduce the nickel content to 0.505 percentage. So this is very good because you have very less nickel. So the probability of toxicity effect is minimized, or toxification may be minimized after the implantation. So if you see the corrosion result, you will find that the 316L steel, 316L8 stainless steel having 0.151 nitrogen content. This is having highest corrosion resistance, pitting corrosion resistance. So nitrogen not only replaces the nickel and hence offers the good general corrosion resistance, but also it offers very good pitting corrosion resistance property, because at the site where there is that the pitting formation is because of bleaching of the chromium oxide film which forms on the surface of AISI316L stainless steel. So when nitrogen is there in the steel, it basically forms ammonia. So just changes the environment from acidic to that basic, and by that process it basically increases the that pitting corrosion property of the steel, because in that is that acidic bath is acidic bath, particularly if chloride is there in the environment, that is responsible for bleaching of the chromium oxide film which forms on the surface. So crevice corrosion property also, if you see, it is increased, that is the crevice corrosion rate is decreased to a large extent at different voltage when you go on increasing the nitrogen content in the steel. So similarly, if you see the abrasion corrosion, abrasive wear and tribocorrosion property, you will find that the abrasion wear abrasive media in air, and this is sodium chloride solution, you will find that wear value, relative wear value is significantly reduced in nitrogen containing hardness is increased, and hardness after abrasion is also increased, and this is relative wear value actually is significant. This steel is showing it is higher value, but this particular C16L, but this bio SSN4 is having more or less similar value as that of a little higher value, but I do not know, but as such, as hardness is little higher, so it should offer higher abrasion wear as well as tribocorrosion performance, but it's not showing so hardness, if you say after abrasion it is increased, but abrasive wear value is not really. So these are research results. So someone can always see the take the nitrogen containing steel and see the effect of this nitrogen on the tribocorrosion property in a little I mean extensive fashion. So if you talk about the SN curve for the nitrogen containing steel like bio SSN4, you will find that is that fatigue property is also significantly higher in case of nitrogen containing steel than that of without nitrogen content. So it improves fatigue corrosion resistance property to a large extent, it increases the corrosion resistance to a large extent, but tribocorrosion property, why it is showing poor value, we have to, someone can repeat the result and check what is the reason behind it. So again, this is showing that after 7 days how the cell is growing. So it is shown that it is not visible over here, but if you see the report over here, it is shown that nitrogen containing steel, the cell viability and proliferation rate is higher than that of other 316 cell stainless steel. Now, if you talk about surface structuring, if you talk about osseointegration, so osseointegration can be achieved by two ways. Number one is by development of bioactive coating, and number two way is by the roughening of the surface. Another approach which is followed prior to implantation of the metallic implant is by sand blasting. They do sand blasting, short pinning prior to application of the implant in the human body. So when sandblasting is done, it causes lot of rough sides on the implant surface, rough grooves on the implant surface. So when grooves are there, cells get anchored on the surface, because all bioinert implant materials, particularly titanium based material or AISI316 stainless steel, the mechanism of cell adherence is because of the mechanical anchorage, not really any spontaneous action. So they do bioactivation of the surface by two ways. First way is by mechanical roughening. Second way is by application of bioactive coating. So if you talk about coating, then there are so many different varieties of coating techniques that are available. And while application of the some coating, material coating, you have to choose the proper coating technique. That's very important. So in the next few slides, I would like to show the effect of plasma spray deposition of this hydroxyapatite coating on the surface of the implant, and also we will just try to show the effect of we'll try to replace the sand blasting with that of laser surface texturing for improving the bioactivity of titanium based implant. So now, as I mentioned you, that bioactive coating on TI6L4B for improved osseointegration, where we used two different types of materials. Hydroxyapatite is very common materials, which is basically applied on the surface by deep coating or by sol gel coating, but we use plasma spraying technique for development of hydroxyapatite, but a little bit modified hydroxyapatite, because hydroxyapatite is very soft in nature. It gets dissolved to a very large extent. Dissolution rate of hydroxyapatite within human body, in human body fluid, is very high. So yeah, in addition to that, hydroxyapatite is also the wear rate of hydroxyapatite is also very high. It is very soft in nature. So we tried to modify the coating by addition of titanium dioxide and zirconia. So instead of pure hydroxyapatite, we developed the composite coating having 50% TiO2 and 10% ZrO2. And obviously this TiO2 and ZrO2 were reported to improve the strength, and dissolution kinetics were not reported properly. So we developed these two coatings by, in addition to 100% hydroxyapatite, which was a standard, by plasma spray deposition technique. So we also did heat treatment operation for just crystallization, because whenever we did plasma spraying, it was typically amorphous coating. So we did heat treatment so that it gets crystallized, and then we characterized the plasma spray deposited structure, and then evaluated this mechanical and mechanochemical as well as cell adherence study. So if you just see the structure carefully, you will find that this is the 50% TiO2 composite coating, and high magnification view of different zones are shown here. So we find that this plasma spray deposition leads to development of completely dense coating. So density wise it was 95 to 96%. Few porosities were there. So, and obviously at high magnification, if you see, you'll find some micro cracks are also present. So as we have added these things, plasma spray had a 50% TiO2 composite coating at high zone 5 and this is high zone 4 and zone 5. So what is happening is that when we just when we added it, this is after this microstructure is after dipping actually. So whenever we dipped it in the tricalcium phosphate, that hydroxyapatite solution, then there was also that tricalcium phosphate deposition on the surface of the hydroxy, this deposited material. So the tricalcium phosphate deposition rate was increased in that 50% that composite coating as compared to that of as received hydroxyapatite. And this is plasma spread hydroxy composite coating on TSA after heat treatment. So after heat treatment we saw there was a little bit crystallization of the coating. So we found there was also little grain growth phenomena also, and stress relieving operation was there. So other coating was highly stressed, but whenever we did had that heating operation, then stress was completely relieved. So that was one of the interesting feature of that typical heat treatment operation. So in the other case, when we did zirconia coating, where we found that there was again coating that zirconia particle size was very small. So we find very fine particles of zirconia in addition to hydroxyapatite, and phases on the surface. So this is there are also some porosities which are present in the microstructure. So scanning electromagnetic again had 10% zirconia composite coating. So after heat treatment we saw very much at high magnification, very spongy kind of appearance was observed, which was like hydroxyapatite actually again reacted with zirconium, then calcium zirconate formation was there. So these calcium zirconates were also very fine nanostructured in nature. In nature. I'm sorry, I did a mistake. So this was not. This is while this was calcium hydroxyapatite from hydroxyapatite actually reacted with TiO2, and then there was formation of this tricalcium phosphate. So this was not after dipping. So when this was confirmed by transmission electron microscopic observation. So we see that there was presence of calcium zirconate and calcium titanate phases in the structure, which was confirmed by SAD mapping. Similarly, the calcium zirconate was also confirmed by TM observation. So now if you quickly go through the mechanical property of the coating and corrosion resistance property, you will find that due to addition of TiO2 and ZrO2 both, there was significant improvement in corrosion resistance as well as there was the Young's modulus of the coating was reduced as compared to as Ti6L4b. But if you talk about the corrosion rate was again not really so high as Ti6L4b because of higher dissolution rate of the hydroxyapatite. But the pure hydroxyapatite results are not there when we compared it with pure as received HA coating. We found that dissolution rate is decreased as compared to only HA because of the presence of TiO2 particles. So because of hydroxyapatite coating, the corrosion rate or dissolution rate of the surface actually decreases because of the higher dissolution rate of hydroxy. So hydroxyapatite though offers bioactivity, but it doesn't really offer good corrosion resistance of the surface, though it is not required because hydroxyapatite is bioactive in nature. There doesn't cause any toxic effect in the human body. So then if you just quickly go through the mechanical properties, we find that mechanical properties of the coating is lower than that of adhesive Ti6L4b in terms of Young's modulus and also plastic energy. So but this Young's modulus reduction again is good because on the surface the stress ceiling effect is minimized. So if you see the bioactivity behavior, we found that bioactive, as it is hydroxyapatite, certainly as such that hydroxyapatite is bioactive, and in comparison to that, because of addition of TiO2 and ZrO2 particles, there is not much deterioration in bioactivity. This is the surface microstructure which is shown over here, but we actually determined it by weight gain, by the weight change measurement. After each hours of dipping, we found the amount of weight, that is the amount of rate of weight change as a function of original weight. So partly there is weight loss because of dissolution, and weight gain is because of deposition. So what we found is that area fraction of deposition after dipping is 22% for Ti6L4b. However, due to hydroxyapatite coating, it is 55%, and after heat treatment, you find that there is a little bit reduction in the area fraction of the apatite formation. So there is a little bit reduction in the bioactivity, but these are all experimental results, and bioactivity is a crude way of measurement of the bioperformance of the material. So we have to go for in vivo analysis to know how is it anchored to the tissue, hard bone actually. So now we also try to improve the osseointegration property by surface texturing. So usually, as I mentioned you, that people do apply sand blasting, but whenever you do apply sand blasting, there is a random roughness on the surface, and that random roughness on the surface causes cell growth in a random fashion. So we try to observe the effect of periodic structuring or periodic roughening on the surface, and its effect on cell attachment. So we use laser ablation technique. So the process is called laser surface texturing to just cause the periodic structuring. So where high power that nanosecond laser was employed on the surface to ablate the material from the surface, and subsequently raster on the surface to cause texturing, and we tried to develop these two different types of texture. One is linear texture, another one is again group texture. So in one kind of texture here, basically we remove the material in a spot by spot fashion with the diameter of each groove of 20 micron. But here again in a linear fashion, in both cases we covered almost 50% of the area which was textured, and 50% of the area was untextured. So this is a typical parameter. We also change the environment. In one case we use argon, other case we use oxygen, and along with laser treatment, and third case we use nitrogen. And also our the standard was sand blasted sample. So sand blasted sample was also done in order to understand the effect of that periodic texturing or added advantage of periodic texturing over sand blasting. So the textured surface, if seen at a very high magnification, texturing was conducted in air. So we find that very small nanodots of oxygen was observed on the surface, and this kind of fine oxides are beneficial because it improves the firstly it improves the mechanical performance of the surface to a large extent in terms of wear and corrosion. And second added advantage because of the oxide formation is that it increases the bioactivity of the surface. Because titanium, as such, titanium surface, whenever it is implanted, there is oxide formation on the surface which is spontaneous in nature. But that spontaneous oxides which form on the surface, that is very much loose and porous. So as a result of which it doesn't perform the way it should have performed. So that's as a result, in order to improve the performance further, people do use different surface oxidation technique like anodization, surface high temperature oxidation processing. So here while processing we had grain refinement as well as very fine oxide particles dispersion all throughout the surface. These are all beta phases. There was redistribution of the beta phases as such during in adhesive Ti6L4V beta are there along grain boundaries, but when we melted it there was vanadium redistribution, so the beta phase was discontinuously present all throughout the surface. When we melted in air nitrogen environment, we found that oxide formation is there, but surface is again oxides again, and partly oxides, partly metals, so oxide networks are there. Similarly, nitrogen environment with which when we melted, we had titanium nitride networks, and in addition to that, there are titanium, alpha. So in linear textured surface we found, as I said, that there is in oxygen environment very thin oxide film was there on the surface, which was basically in air again we did in three different environment, air, oxygen and nitrogen. So here we find patches of the oxides present, and oxides in the form of very fine uh, dots precipitates, and nitrogen environment again nitrites are also present all throughout the surface. Oxygen environment we find lot of oxides on the surface. So these are actually confirmed by TM analysis, and we further reconfirm the presence of these oxides by backscatter diffraction spectroscopy. So this is typical phase mapping using EVSD analysis, where we show that there are presence of beta and alpha linear textured argon surface in argon environment, and if you see carefully you will find that this is mostly alpha. Some amount of rutiles are also there, oxides are also there, and Ti6O, this another oxide phase is also present to a very small amount, and beta are there in a discontinuous fashion. A circular texture surface again. This is the texture surface. We find the cross section we are observing actually. Here also you see a lot of that rutiles are very less, but this alpha is mostly alpha and Ti6O phase formation. So phase stoichiometry varied with different samples actually. So here again argon and oxygen environment we see a lot of beta phase, alpha, mostly alpha, and uh, and some oxides are also there. Red particles are very small oxides which are present on the surface. In nitrogen environment there are a lot of nitrites, and alpha phase are also there. So these are a little bit again EBSD. We try to just map the phase, but this is again a little bit you can say that relative measurement technique. We try to see actually, but had to be confirmed by it was confirmed by EDS analysis rather, to know whether these are actually these phases. So when we did XRD analysis, we found that in oxygen containing environment, when we did the argon containing environment, oxygen containing environment, in oxygen containing there are a lot of oxides on the surface. Nitrogen containing environment there is again nitrites. These are all typical analysis research results. So but what is important here is that there was residual stress as textured condition. There was also residual stress, but that was not significant. That was below the accepted, much lower than that of within the acceptable limit. So this whatever residual stress we observed in the, because these were irradiated using nanosecond laser, very low pulse nanosecond laser, so it didn't cause any high residual stress to be introduced on the surface. If you see the Young's modulus was significantly a little bit higher than that of adhesive because of presence of oxides, nitrites, dissolved phases, and hardness was also improved to a large extent because of oxide and nitrite phases on the surface. Due to these all things, there are improvement of wear resistance property. These are dry wear, but this is not. These are the results which we observed long back. So these days we are not doing any dry wear study. We are trying to understand the performance of the coated material by by tribocorrosion, where we are doing the same fretting wear in presence of the hang solution. So, but we are getting the more or less similar trend. Whatever we get in dry wear, similar trend is observed in wet wear as well. But obviously, there is corrosion effect is also combined in wear. So that's also very good information on how the materials behave in real environment. So we find that in nitrogen environment the wear volume is lower than that of as the argon environment, argon textured samples. If you see the microstructure of the wound surface, you see that this is typical fretting where that characteristics of fretting wear is observed over here. And interestingly, if we just see the corrosion rate due to texturing, it was observed that corrosion rate was significantly reduced on the textured surface as compared to it is too much reduction in the corrosion rate. But this reduction obviously is not only for the textured surface. This corrosion study was done on the surface where there were combination of both textured and non-textured surface. So possibly area corrections were not done. So whatever we took average area, average surface area in corrosion area is very important. So area calculation is very important, but we just did the average area calculation, but actual area is whenever you do texturing, it is much higher than that of average area. So whatever corrosion rate is observed, actually that is though a kind of composite area. First error is because of the fact that this is not truly on the textured surface wear value, corrosion value or wear value as well. This is a combination of textured and non-textured surface. And second problem is that while calculating the area, so we just calculated the average area but not really the actual area because of the presence of the texturing actually. So these two corrections you have to make and then do a little bit calculation and then find out what exactly the true wear and corrosion rate of the textured surface. But in actual situation it's of no use, because actually you will see whatever is shown over here only, because it is a combination of actually combination of texture and non-texture. 100% texturing uh, cannot be done here, because then it is no more texturing, it is ablated surface. So if you see that this hydroxyapatite deposition rate, you will find that hydroxyapatite deposition rate was also higher in textured surface as compared to that of we saw actually as received surface. And this was confirmed by this analysis, that is typical XPS XRD analysis. And if you see the surface energy, we saw that surface energy was varied for circular textured samples to that of that if you just see surface energy was lowest in circular textured sample or dimple textured surface, but it was highest in case of if you say that linear texture sample in argon involved in oxygen in air environment. This is argon, nitrogen, argon, oxygen, nitrogen, argon, and this is air. Though, so what this is also important because surface energy is minimized here, though it's comparable to that of a as received sample. But what we saw that here also that weightability, when we observe the weightability is also too much lowered here because it's not weightable at all. So it's offering good corrosion resistance property. But if you talk about cell attachment point of view, weightability is also very important. Higher the weightability, higher will be the cell attachment. So this is typical cell attachment behavior of the this as received sample again where we use 3T3 cell as the cell for attachment cell media. So it was random, it was uniform all throughout. But when we just compared it with sandblasted, we saw that on sandblasted samples, though people use sandblasting, but it was not really very strong and uniform, and it was also quite percentage cell adhered is also much lower than that of these adhesive samples. When we did texturing, then we found that nitrogen textured samples offered maximum adhesion of the cell, and cell attachment was parallel to that of the textured surface. So wherever there was texturing there, attachment was adhesion was maximum. And in cellular texture sample, what we found, the circular texture sample, what we found that inside the circle or group, there was not much attachment of the cell. So when we found the proliferation rate, we found that nitrogen atmosphere offered maximum cell growth rate as compared to that of even sandblasted and as received sample. And circular group sample didn't show much promising result. And so we found by texturing what is the way out is, I mean, what is the takeaway of that particular study was that linear texturing was much promising technique for improving the cell attachment and proliferation behavior, cell proliferation and growth behavior, and also it offers very good corrosion resistance and tribocorrosion property. We took the work further and we did a lot of nanosecond and femtosecond laser surface processing. So those laser surface structuring, those lasers I could not show here because of lack of time actually. So we had I tried to gather information. So what I had earlier, those PPTs are also not prepared fully because we did a lot of paperwork and then I didn't present anywhere. So now this is another study where laser surface micro laser, I mean where continuous wave high power laser was applied for surface melting, and we did it on titanium as well as AISI 316L stainless steel. So this is the typical result on AISI 316L stainless steel, where we used typical diode laser for surface melting purpose. So for laser surface processing, I see Professor Misto is there. I hope he is still around. So I mean he is very much stalwart on laser surface processing. So laser beam, whenever you irradiate on the surface, there is problem of reflection. So around it was for diode laser, we saw that it was around 80 to 85% light is reflected. So we had sample preparation by sandblasting operation, and then we did laser surface melting using argon and also nitrogen as media, shrouding environment, and we did all kind of characteristics and testing. So this is a typical laser surface processing where we use argon and nitrogen as media, and power was varied from, these are optimum parameter. One of the interesting surface interesting observation of on laser surface processing is that you get very good result only when you do processing under a very narrow processing regime. Narrow processing regime means narrow laser power and scan speed combinations. So people do often ask, the viewers do ask rather, why didn't you choose higher power and lower scan speed? These are all other parameters. But in all cases, we find that even though you use thousands of parameters, you'll find that you get best result only under a few on only a very narrow power scan speed combination regime. It's not power, rather power density, narrow energy density regime, you should say. So here we did argon and nitrogen as environment and did processing. Excuse me, I got cold because last few days I was traveling and then somehow I had infection. So argon was it's okay, sir, madam, no problem. So the power range was from 0.75 to 1 kilowatt and scan speed was 0.05 to 1, and your in that beam diameter was 2.5 to 3 millimeter. So I'll show the results of surface melting of 316L stainless steel. We find that after surface melting, you see a lot of refinement of the microstructure. This is in argon environment, and this is for nitrogen environment. So in nitrogen environment, we see that so this is argon environment, and these are nitrogen environment. So we find that in nitrogen environment there are formation of very fine nitrides of Fe2N and also chromium nitride. So this is interesting in case of this concept, surface melting. So laser processing is so unique that you can do anything using this laser on the surface. So particularly we saw very interesting results on surface melting. Whenever you do surface melting of alloy system, you just introduce refined microstructure. In addition to that, you just go on redistribution of the alloying element in such a fashion that there is homogenization of alloying elements all throughout the microstructure, which is not there in edge cast and rod product. So this homogenization and refinement combiningly introduce or cause lot of improvement of different properties, particularly corrosion resistance property. So this philosophy we applied in many alloy systems, and where we got the similar result. So it's very easy technique. You are simply melting it, and in one case you are melting argon. So when you use argon, then naturally there is refinement of microstructure, and that rate of refinement depends on the argon flow rate as well. So as you go on increasing the flow rate, your convective dominated heat flow also increases. So cooling rate increases, as a result of which degree of refinement also increases. But when you use nitrogen as environment, there also you just introduce a lot of nitrides in the structure. So depending on the material which you are using, we saw in titanium, 3 or 6L stainless steel, mild steel, everywhere we found very fine. And interesting feature is that the nitride what you get here, it is really very high volume fraction of nitrides, which is otherwise not possible by conventional diffusion assisted surface nitriding processing. And these nitrides are highly refined nitrides. So they are kind of composite structure consisting of very fine nitrides distributed all throughout. So because of this structure, it offers a significant improvement in wear resistance as well as corrosion resistance property too, because nitrogen also is very good element which always offer improved corrosion resistance property. So these are the different effect of the environment on the melt zone thickness for different samples combinations of power scan speed. So as you go on increasing power, you see that depth of melting increases. As you go on increasing scan speed, depth of melting decreases. So these are very common observations. So but what is interesting is that you find that there is significant improvement in hardness both in argon as well as nitrogen environment. Nitrite formation is there, but it was not really so high, so we get a little higher hardness when we do melting in nitrogen environment. So as a result of which there is also increase in wear resistance property. There is a significant decrease in wear rate for both cases, and mechanism in all the cases. What we do is that we don't stop over the observation of the kinetics. We also try to understand the mechanism and give a little bit schematic on what's happening inside at the contact zone in a manipulated fashion. So if you see the corrosion and wear and wettability rate, you will find that in argon and in argon and nitrogen environment, if you see the E core value, you will find that E core value also shifts towards noble direction as compared to that of as received AISI 316L stainless steel. So pitting corrosion, normal corrosion tendency or maybe reactivity decrease, overall reactivity of the surfaces decrease, and EPIT value also is significantly shifts towards the noble direction. So you can say pitting corrosion resistance is also improved significantly for both argon and nitrogen environment. In addition, the overall corrosion rate. If you see the contact angle, you will see that there is also that contact angle doesn't change much, though it is lower than that of as we said substrate. So it is wettable, surfaces wettability increases. But more interestingly, if you see bioactivity increases to a large extent as compared to that of as received. Excuse me. So this is so these are the interesting finding. So this we also similar studies or similar philosophy was also followed in Ti6L4V. So where we got significant improvement in wear resistance, corrosion resistance, and bioactivity. So those results I'm not going to show over here. But another interesting observations we did or I'm going to share here, that is that laser surface cladding of titanium on 316L stainless steel. AISI 316L stainless steel is much cheaper than that of your Ti6L4B or any titanium based alloy. But problem is that they are nickel leaching and higher corrosion rate is are the problems. In addition to that, stress sealing effect. Obviously, stress sealing effect is the I mean you can say the core effect actually, which you cannot avoid by surface processing. But still, if you do develop a very thick clad layer of titanium on Ti6L4V on AISI 316L stainless steel, then corrosion problem can be addressed to a large extent. So with this concept, we basically cladded titanium on AISI 316L stainless steel. But one of the biggest problem of cladding was that there was formation of iron titanium, I mean intermetallic formation. So that problem, iron titanium, Fe2Ti, Fe3Ti, these all intermetallics are of major concern, because those intermetallics can cause problem when the component is subjected to fluctuating loading, particularly in fretting or fatigue wear. So this is the typical top surface of laser surface clad 316L stainless steel with Ti6L4V. So we find that on the surface there was typical alpha beta structure. There is no flaw or no defects on the surface. So this is perfectly flaw free. And interface also, if you see carefully, you will find that there is minimum dilution at the interface. There is nothing, no dilution at the interface, but and also there are no defects on the interface, that is quite crack free and defect free. And we saw that there is a, when we just measure the other properties like micro hardness, we see that micro hardness was higher than that of as received, not because not because materials wise micro hardness, but as such TI6L4B is highly defined whenever you are developing it on the wrought stainless steel. So stainless steel was wrought and wrought structure, but so on the surface it was TI6L4B, which is melted, laser melted. So the microstructure was highly defined. So as a result of which there was improvement in micro hardness and also wear resistance to a large extent. So when we did the corrosion resistance property, that corrosion property was also improved in case of titanium, like this is as received B is the as clad Ti6L4V, and C is laser lased interface. So in the three cases we find that at the interface also the that corrosion resistance corrosion rate was quite low. So interface we assume that possibly there would be galvanic attack at the interface and hence corrosion rate will be deteriorated, but it was not so. So after 7 days of dipping in SBF solution, we find that there are calcium phosphate deposition. Uh, it was more in Ti6L4B clad surface as compared to that of as received surface. These are two different combinations actually. It is interface and this is surface. So interface and surface was of similar in nature. But this is the interface at the titanium rich side. So these are the some of the observations, like clad layer was alpha prime titanium and quench. So this alpha prime is always there when we melt Ti6L4V using laser beam because of very fast cooling. The interface consists of fine equax rates of alpha. In addition to that, there are presence of FETI phase. Wear resistance property are significantly improved. Corrosion resistance is also improved, and bioactivity is increased from the 33.34% for as received to 81% for. So this is also very interesting way of designing the implant by combination of two materials. Like core is having very cheap and then formable core, and then on top of that, because AI316 stainless steel is highly formable, weldable, and also it's cheaper as compared to that of Ti6L4B. If you have Ti6L4B surface and AI316 stainless steel core, then that would obviously give a very good economic way of having the very good implant materials. So finally, it is very important that you design the surface carefully for the mitigation of the or improvement of the properties as you are looking for, and you can use any of the approach, but whenever you follow any approach you have to see the cost consideration as well as you have to also check the environmental impact of the processing. Like for example, you can use chemical route or thermal route or maybe laser processing route, but which one offers gives minimum uh, impact on the environment, or maybe which one is greener, that you have to take care of. And then obviously budget is also major concern. And finally, it is very important that implant designing should be made in a tailored fashion. So and also same modification modification cannot be applied all throughout. It should be functionally graded implant so that you get different process. You apply different process in different zones. Like this is typical optimum biodesigning of implant, where You can use here like surface texturing. Here you can use again surface texturing, and here there is no need. So like that, you have to design the implant in a very much methodical way and wise way. So other things what we are doing in the group is that we are developing porous graded composite and also porous titanium for bioimplant applications, and we are doing surface nanostructuring, shock pinning. We had recently, some good work on shock pinning as well as combination of structuring and that of surface composite surfacing. So those are the things we are doing for improving the overall performance of the implant material in terms of you can say that mechanical, mechanochemical and also corrosion properties. So before just finishing, I would like to convey my thanks and regards to Professor Acharya. It was really, indeed very nice to have kind of invitation from his side and from the INAE Bhubaneswar chapter. So I'm sorry today I had a little fever since last few days because of a lot of travel since the last few days, and it is just there is a season change somewhere. It's very cold somewhere. It is very hot actually. So possibly there is some problem in my communication. So I'm thankful to Prashu Barna. That time he was IIT Kanpur, so very old. Now he is in BIT Vesta. My collaborators are Dr. Mondol, uh, MP Hooper, and my students were Dr. Renu Kumari, Arun, Amit Bishwas, Dr. Dilip. They all did work on this titanium and continuing research, and GST and DBT for partial financial assistance. Thank you so much. Thank you. Now I would like to invite questions from your side, please.
Thank you, ma'am. I invite questions from the audience. Please unmute yourself.
Yeah.
Yes, Tripathi sir. Namaste, sir.
Namaste, namaste.
Yes, sir.
Yes,
Mr. Sanat
Sanat
Kumar.
Kumar, sir. Yes, sir. Please.
Please, sir.
Can I ask now?
Yes, yes,
Yeah,
yes,
Sure,
sir.
yes,
sure.
sir.
Please.
Okay. As a mechanical engineer, I deal with components which are much bigger than what you are. Say a
Yeah.
minimum of 10 millimeter diameter and things like that. But we also do surface treatment. So on the topic that you gave, I found some 2 or 3 very interesting points. One is wear resistance you were talking about. One of the things for wear is a mechanical loading. So
Yeah.
I am wondering whether you are taking that into account. For example, when you put an implant and it rubs against something else, the load between the wear parts might make a difference to its wear resistance. So I
Yeah.
wonder whether I have no idea at all about your implants. So I am just extrapolating from my knowledge into that. That is number one. Number two is that we find that wear resistance is very much better if the hardness of the base material is very high. So you are using 316L, which is in our opinion is not very hard material. It is stainless steel 316L is fairly soft. We use a material called, it's a precipitation hardening material, 17.4 pH stainless steel. It can be precipitation hardened and it can be heat treated to as much as Rockwell 32C. We can have it, and then on top of that we chromium plate or we nitride. These two things we do. When nitriding is also, as you said, produces chromium nitrides. That's correct. That same thing happens. But when we nitride in a gas nitriding, it after nitriding 36 hours or something like that, it produces a white layer on top of the nitrated surface. So we do a glass shot to remove that layer, because that layer is oxide layer. We remove that and it becomes much better. Finally, after nitriding, if you do a grinding operation, if you make it very smooth, then wear and corrosion are much better. So you have a surface finish which is very smooth after nitriding. So I don't know whether these help you in any way, because I have no idea whatsoever about your implant sizes. Thank you.
Yeah, thank you very much, sir. So first thing is that what 17 for a pH steel, that particular steel cannot be applied in this particular case, but 316L stainless steel is the only choice. That's what we did this operation on 316L stainless steel. And gas nitriding certainly could be a better choice, but gas nitriding takes a lot of time, and also it's a very lengthy process. So we tried to replace it using laser processing, laser surface nitriding. So where in laser surface nitriding we could also avoid the white layer formation as is observed in normal nitriding. So because that is structure is not really monolithic nitride layer, this is nitride dispersed layer. So dispersion of nitride was beneficial in improving the wear resistance to a large extent without sacrificing the toughness. So that's how possibly gas nitriding could also be done, but I haven't tried that. Thank you. Sir, can you unmute? Sir, can you unmute, please? You are not audible.
You make the surface very smooth after
Yeah.
nitriding. That will improve corrosion resistance as well as wear resistance.
Yeah,
If
it
that is
was smooth
possible,
because
if
we
your
polished the
component is
surface.
capable of smoothing, if that is possible.
Sir, we polished the surface after nitriding.
Okay, okay.
Because after laser processing, it is a little bit rough surface.
Yes.
So we cannot use it as processed condition. So we polished it mechanically, but it was not really much. So machining was not really too large. I mean, thickness was around 25-30 micron like that.
30 microns, okay. We also do nitriding to that extent only, 30 microns, 30,
Yeah.
35, 25. We actually might do nitriding to a greater thickness and grind it down so that 30 microns left. Because if you leave it too thick, it will break. It will,
right.
It will crack up when in action.
Yeah.
Thank you. Thank you.
Okay, sir. Welcome. Bye.
Professor
Any
Mishra,
other
would you
questions?
like to take a question? Please unmute yourself. Professor P.K. Mishra. Please unmute. Hello.
I think sir is not having question.
Because
Professor Majumdar,
Yes, sir.
Hello?
The Kulmani Gada, sir.
Yes,
I have a
sir.
small clarification.
Yes, sir.
To improve the wearability, flexibility, tunability, is there any process to do surface polymer coating?
Surface
Polymer
polymer
coating.
coating is sorry, may I, yeah, any other question, please, sir?
And a polymer coating, just like you are nitriding or other treatment you are doing, polymer coating, is there any process to increase the lifespan of the implants or flexibility, wearability of this implant?
Oh, you are talking about polymeric material, no?
And polymer coating on this titanium surface after
Polymeric
making rough.
coating. Yes, sir. Polymers are usually quite soft, so it cannot be applied for wear resistance applications. But we are also going to apply very thin polymeric coating for antibacterial property enhancement. So that is very thin atomic 1 or 2 atomic layer deposition on the surface, so that there is no biofouling corrosion. So, but this is not applied for wear resistance applications. Polymeric coating may be done. For example, some polymers are very good antibacterial property. So if we apply it on the wounds where high wear resistance surface, it offers better biofouling corrosion resistance. So, but we haven't tried that. We are going to try that. But polymeric coating cannot be applied for wear resistance applications, sir. So is that okay for you, or do you have some other queries, sir?
No, it's okay for me. Suppose nowadays people are working with graphene-based composites.
Yeah.
Graphene-based composites such a bioimplants.
Yeah. Graphene-based composite people can use because graphene offers very good lubrication property. So it also offers wear resistance. Graphene is good. I mean, a little bit graphene if you add along with the this thing, but we did laser processing. So in laser processing, we cannot apply any graphene composite because graphene will be dissociated.
Okay, thank you, madam. Thank you,
You are
madam, for the
welcome.
clarifications.
Yeah.
Any other question?
Yeah, Prashant Mukhopadhyay said, thank you so much. It's very nice that you are here. Prashant Mukhopadhyay, you have any question?
Hello.
Sir, I don't think there is any other questions.
No, Tripathi here. I just have to ask a very general question. We have done so much work on these implants, and have you transferred your technology to any manufacturing medicals, pharmaceutical or something, and is it used in the country, or we are importing all the implant materials from abroad?
Sir, no, I don't have any. So far, I'm looking for a good collaborator or manufacturer. I mean, we are writing a big project where we are looking for good manufacturers. So, mostly people do import it from abroad actually. So whenever I ask for anyone, they say we have imported like Johnson and Johnson. They have they just they are very good distributor of implant materials. So when I talked to them, they said that they have all imported materials. So they have to get the permission from their manufacturer's side. But local manufacturers said they do develop the implant for this not for human body, but they do develop mostly for animals actually. So I'm possibly I will be collaborating with them only to see the kind of results they are getting in animal, like different animals like cows and these thing goats. They also use implant materials. So possibly similar results will be observed. But human implants they are basically all are imported. So but in hospital, there are many other implants also applied, like fracture fixation devices. So where if there is any fracture, they use some support for fixation purpose. So some gap is there, so deformation is there. They try to use some implant for that. So for that purpose, we are developing some titanium foam. So that we have a very good doctor. So they are saying collaborated. So he is saying that as it is proven, so we can always use it for that purpose. So clinical after a little bit clinical sterilization process. So that's how our status is. We haven't talked to any of the implant manufacturer abroad actually, but abroad possibly they are using many other coating technique for improving the performance. I have no idea. So whatever work we are doing, that is up to the whatever up to the standard or maybe a bit higher than that of research standard what is actually what are established, but we haven't applied it to any manufacturer especially who are developing the implants for human body.
Actually, do you benchmark your results with results from abroad or actual manufactured product from abroad? And let us say knee transplant, whatever you put, the ball and socket joint and all that. Why don't you tie up with a industry to manufacture and benchmark product to product?
Yeah, that's what we are looking for collaborator. That I said you that is it's very difficult to have the industry partner for that actually. And implant manufacturer also implant means if you talk about lifetime of implant, that is usually 9 to 10 years actually, titanium based implant.
Yeah.
So after that, if there would be any increased lifetime or not using our things, that is also very interesting to know. But I haven't done it. I have to do that, right? It's very important to just make yourself like your technology important to the market. You have to do. There is no other option. So I'm looking for you. If you could help me, that would be of great help for us, sir. Particularly in hospital, SOA University is also having in-house hospital. I guess if there is any, I'm looking for very good collaborators. From the hospital side as well, doctors, because I had a doctor collaborator in West Bengal, but they are not really interested to take the, I mean they are a little bit afraid to take the this thing risk of using this particular technology, because they are, whatever they use from the market, that's what they are willing to use it. So it needs some, I think there are some methodology which needs to be followed for using it in human body. So that's what they are, they said it is our limitation, so we cannot apply that in human body.
I
Okay,
still
thank you,
find
ma'am. Thank
actually
you.
Professor Misra
Thank you.
raising 3 questions.
Sir,
Mr. P.K. Misra.
yes, sir,
Unmute.
how are you?
Misra is a giant in micro manufacturing, and
That's what he
Yeah,
only told me today. That such a, but he is not actually
he's not unmuting.
unmuting
Actually,
himself.
he's still muted.
No, sir is not unmuting. Sir, kindly unmute yourself.
yeah, he is raising the hand. Sir, where are you?
Okay, let me contact him on phone.
Yeah.
Madam Adarsh has raised a question that I have a query regarding textured surface that show enhanced corrosion resistance even after increasing surface roughness, which is opposite in nature.
No, actually in texturing what's happening is that there is highly refinement of the microstructure and also very thin oxide.
ହଁ ସେଟା ତ ଆପଣ ଟିକେ ଅନମ୍ୟୁଟ୍ କରନ୍ତୁ, କ୍ୱେଶ୍ଚନ୍ ଟା ରେଜ୍ କରିପାରିବେ, ଅନମ୍ୟୁଟ୍ କରନ୍ତୁ। ନା ଆପଣଙ୍କର ଏଇଠି ଟିକେ ମ୍ୟୁଟ୍ ଅଛନ୍ତି, ଆପଣ ସେଟା ଅନମ୍ୟୁଟ୍ କରିଦିଅନ୍ତୁ ଟିକେ। ନା ନା ସେଇଠି ଯୋଉଠି ଅଛି ଏଟା ଦେଖୁଛି, ଦେଖନ୍ତୁ ଏଠି ଗୋଟେ ଥିବ
କ୍ୟାମେରା ଆଉ ମାଇକ୍ରୋଫୋନ
ଜଷ୍ଟ କ୍ଲିକ୍ କରନ୍ତୁ, ଯେ ମ୍ୟୁଟ୍ ଦେଇ ଠିକ ଅଛି। এইଠି ଉପରେ ଅଛି, ଦେଖନ୍ତୁ ମାଇକ୍ ଯୋଉଠି ଅଛି ଏଠି, ସେଇଠି ଗୋଟେ ଅଛି ଭିଡିଓ, ଆପଣଙ୍କର କ୍ୟାମେରା, ଆଉ ଗୋଟେ ଅଛି ମାଇକ୍ 5।
So maybe Prashant Mishra is facing some problem actually. But from administration side, you can solve it.
Vivek, you can do it.
Yeah, I think you can do it remotely, no?
No, Vivek.
But my slightly different. Yankee, our laser is happening only. It is laser instead of Japanese. The specification we cannot use for bioplant anything more than 75 watt laser. তারপরে সেটা এক্সপ্লেন করে দেখেছি when you have a focus laser, then focusing zone to তলুকু, that means defocusing zone better work করে than the converging zone.
So, madam, are you able to hear what he is saying?
No, sir, it's not actually, and I didn't follow it properly. So he was asking from some power selection.
Oh,
regarding
75 watts. He's saying 75 watts is the maximum you can use on the laser. That's what I heard. Of course, I didn't follow Bangla, but I think 75 watts is the laser power. That's what he was saying.
75.
You, for surface texture, especially for a bioplant, you cannot use more than 75 watts laser. Again, while doing so, you have to avoid the converging zone. Diverging zone you have to go. And again, another one thing, for this sort of plants, in the defocuser, you have to do underwater. Under a colonial source. Anyway, we'll talk to you. I will value.
Okay.
Okay.
The surface preparation has to be done
Majumdar,
underwater,
actually,
he says.
He will be in
Surface
touch with
preparation
you.
has to be done underwater.
And,
No, sir, underwater processing is different processing. We cannot do it. I didn't do any underwater processing. We didn't do any sock pinning. I'm talking about surface texturing. So in sock pinning, we can do underwater actually. I mean, little bit water layer will be there, but we did texturing in air. We haven't used any water, sir.
And any you offline actually you discuss with him.
Yeah,
He
no
has got some
problem.
suggestion.
That's
Okay.
right. That would be great.
In WM University, for what you call this company called I can't remember.
No.
I have proved that one. If you process before the, if you are using a focus or a defocus laser, so we will discuss.
You please discuss because he is
Okay,
not able
sir.
to hear. Okay. Okay. Thank you. So, Professor Josna Majumdar, it was
Yes,
such a
sir.
pleasure that in
Yeah,
spite of
thank
all
you so
your
much, sir.
thing, you could come and give an excellent lecture. And
Yeah.
in spite of actually you are having some throat problem, you still stuck to this point that on 10th actually you will give. So we are really very, very thankful to you for doing so. And now those who are present, please actually you switch on your camera so that we can take a photograph. Okay. Please take a photograph. Done? Okay. So we have done so. Now I'll request Madam Renu Sharma to propose a vote of thanks. And one thing that I would like to mention that we can't really give anything much, but definitely on behalf of this group, we'll send you a small memento by post. Okay? Please. Oh, you are again mute. Madam, you are again mute.
Myself, sir?
Thank you so much, sir. Thank you so much. I am extremely grateful to you for giving me the opportunity to share my experience with you all. And that's the gift for me. That's what I was saying. So thank you so much. Yeah.
Please.
Yeah, thank you, sir. Good evening. It's my pleasure to deliver the vote of thanks for 50th distinguished lecture in this esteemed series, jointly organized by INAE Bhubaneswar chapter, Shiksha Anusandhan deemed to be University, CSIR MMT, Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, and IEEE Bhubaneswar subsection. First and foremost, I extend our heartfelt thanks to the distinguished speaker, Professor Josna Dutt Majumdar Ma'am, Institute Chair Professor, Department of Metallurgical and Material Engineering, IIT Kharagpur, for delivering such an insightful lecture on increased lifetime of metallic bioimplants by surface engineering. Your expertise and in-depth presentation of this critical topic have enlightened us and inspired us for further exploration in this domain, ma'am. I would like to emphasize that we are also having our Institute of Medical Sciences, where we are doing a collaborative research with various other institutes, and especially in the Department of IDS and orthopedics, they are taking care of these things. I would like you to collaborate with Institute of IMS, Shiksha Anusandan University, ma'am. And I would also like to thank our esteemed dignitaries, especially Honorable Chairman of INAE Bhubaneswar Chapter, Professor Damodar Acharya Sir, Vice Chancellor of SOA University, Directors of CSIRMMT, IIT Bhubaneswar and NISER Bhubaneswar, and the Chair of IEEE Bhubaneswar subsection, and other professors from Bhubaneswar subsection like Tripathi Sir, Ganpati Panda Sir, for their continued support and guidance. Finally, my gratitude goes to all the participants, esteemed fellows INA, academicians, researchers, and students have made this lecture a true success. Thank you once again. I look forward for your participation in forthcoming lectures of this distinguished series. Thank you. Have a great evening. Namaste. Jai Hind.
Thank you very much, sir. Thank you. Bye.
So you, madam, actually you take little initiative in connecting Professor Josna Majumdar to our
yes,
dental people.
Definitely. Definitely.
Okay.
Yes, sir. That would be, yes, madam. That would be a great opportunity for me.
Yes, ma'am. We are having
true.
doctors working on it, and I'm going to connect you, ma'am.
Okay. Thank you, sir. Namaskar. Thank you, madam. Thank you, sir.
Namaste.
It was nice. Yeah. Please take care. Yeah. Bye.
Bye.
Bye.